Hello, everybody, and welcome to today's SEBA Techinar. I have the pleasure of joining me several experts from the ONF community that kindly um, uh, came to join us to speak about the SEBA reference design. First of all, there is Burak from Netsia. He's working as a product manager for SEBA, and he's also leading the SEBA Reference Design 2.0 work. A very straight colleague of his is Semil from Turk Telecom. Semil is the senior network architect at Turk Telecom and is involved in SEBA since the core days. Um, then I have Mario from Deutsche Telekom. Mario is professional researcher and development engineer at Deutsche Telekom, and he's working on the improvement of access technologies and realizing the Deutsche Telekom's strategy of transformation into a software telco. And he's supporting the projects in DT to realize the OpenBNG initiative and has contributed the OpenBNG part to the SEBA reference design. I am Andrea Campanella from the Open Networking Foundation, and I will act as a moderator of today's talk. So first of all, I just want to introduce a little bit what are ONF reference design. So the reference design are golden standards for what is deployed in a production network of the operators that join ONF and jointly work on these reference design. Resources from the operators, from the architecture teams, the design teams, and the operations team come together with our community of vendors, supply chain, and partners to craft these reference design and that bundle both the interest of the operators, but also the capabilities and possibilities and offers of the supply chain and the vendors. The idea is that then the operators take the reference design and base their RFPs on these designs. Then at ONF, with the community at large, we develop what we call an exemplar platform, meaning that the reference design is taken as a blueprint for an actual then implementation of it with physical code that uses selected components in open source and is publicly available and is then used by our operators in their physical deployment. This implementation is obviously aligned between what the operator requirements are and the supply chain offering paired together and described in the reference design. The reference design creation process has several steps. Initially, there's a definition and creation phase that is only open to ONF partners. Then we do have a member-only review and comment process after the initial reference design is outputted by the group of the operators and partners. And then there is a general public release. Today, we are talking about the SEBA Reference Design 2.0, which just got released to the wide public. So without further ado, I'll give it over to Semil.
Okay, good evening to everybody who are in this call. I'm Cemil from Türk Telekom, and I hope you can all hear me well. Before I begin, I would like to thank Andre for his introduction. So I want to start with this why this is important for us. As many of you already know, that Türk Telekom plays a pioneer role at ONF projects and supports those platforms on many levels. SEBA is undoubtedly among the most important of these platforms. We provide code support, design support, and documentation support for this wonderful platform, and that's ONF created. Since the first reference design, which we were actively participated and which was published in 2019, we care to emphasize the importance of the reference design in every platform we attend. We believe that it is essential to provide an accessible document that can guide the whole world and telecom industry for a fresh vision of transport fixed access network. We believe that the gold standards defined by ONF, which Andre mentioned, is the most important step of the transformation, and later on productization in open source. It is precisely for those reasons that Türk Telekom stood out for a new reference design and wanted to address yet undefined parts of the platform and wanted to lead the second reference design work. I also want to add that we may be the lead of this reference design work, but we were not alone. And this is basically achieved because of the great team that we had. And you see those key players on this page that jumped in and helped to form this document. Today, we are glad to share that it's publicly available right now. I also want to talk a little about the importance of the productization. We believe concept designs should help to create some end products and should guide for the productization as much as it can. At the end of the day, if we want to have a sustainable platform, it should be used by operators with those products. You will have a better understanding of what has been achieved by this work in the upcoming minutes, but I can say that with the additions being made on top of the first reference design, I think we currently have a much better explanation for a standard product. Because in this document, from APIs to scalability approach, there are lots of new additions being made. And these basically helps this process of productization. I just want to leave the stage to Burak, who was the chair of this design work, for deeper explanation and what's been achieved.
Thank you, Cemil. Hi all, this is Burak genuinely. Sorry for the difference between my profile photo and the video footage. Hopefully I'll be able to get a haircut after, hopefully we can go to normals. So that said, I've been working for Reference Design 2.0 for more than a year now. And Tom was leading the first reference design. So I want to thank him, Tom Moore from AT&T, for his great work that far. And then he handed it to me, and I had the privilege to work with you guys, with the team. It was a very interesting and good work, actually. Thank you for. I want to thank the team for this work and for being able to achieve that far. That said, I want to start with comparing these two architectures of Reference Design 1 and 2. As you may notice, there is not a big difference between them, which is good, by the way, which tells us that we have reached a stable state, by the way. The most important thing maybe that you can notice in the Reference Design 2.0 work is the device manager, actually, is the introduction of the device manager component, which deals with the management of the devices and the monitoring and configuration, which is not specific to the technology, access technology. And also we try to highlight the FCAPS interfaces, which was actually there in the previous architecture, but we want to highlight it and make it more seen, actually. So we can continue with the next. That said, I'm right now trying to, yes, these are the additions that we made, we achieved in Reference Design 2.0. What we have done, we have added MBI APIs, and we have enhanced what is existing, actually, with the introduction with adding definitions and also input and output parameters for managing the pod, OLTs, ONTs, and service management, so that we reached some kind of a more concrete MBI interface there. And after that, we also, yes, that was the interface between the SEBA and the upper pods where we talk with device SPSS. So after that, we also updated what was there in the BNG. We added some deployment options, and that will be told in the next slides. We added the device management there. So actually, in the beginning, that was not in the plan, the device management part. But as it was being deployed in parallel, we decided to take it also to Reference Design 2.0 because there is a requirement for that from the operators. So we added the device management there, where we tried to manage the devices, and we tried to configure them, monitor them in such a style that it is not specific to the technology, access technology. The things that are specific to access technology are done by the SEBA. So the other things are managed by device management interface. So after that, also, what we didn't plan at the beginning, what we have added in the Reference Design 2.0 is the scaling part, where we have added a part for per-OLT VOLTHA stack model. That was also being developed in parallel, so we also decided to put it into the reference design document. That said, we also added two more items. One is the access technology, which is for fixed wireless access, which is kind of an important thing for the incoming 5G and beyond, actually. And also, we added some preliminary use cases which are required for pod lifecycle management, like bringing up the pod, adding, removing, upgrading the entities in the pod, and so on, and also adding and monitoring the softwares and the software entities in the pod. So next slide, please. Yes, this is the part actually where in the architecture I'm showing you that where we added some Northbound APIs and we enhanced what was existing in the previous reference design. So we added and enhanced the existing for pod OLT ONT service management with the concrete definitions and also with input parameters and return values, because we want to implement this Northbound interface as concretely as possible. So that will be helpful for the example platform implementers to make them integrate with the OSS PSS software operators more easily. So next part, please. Yes, these are the APIs actually that is existing in the Reference Design 2.0. We have categorized them in 4 groups, and which are pod management, where we try to, with the defined APIs, we try to provide the inventories of the pod, monitor some hardware resources and status, and do some management for the alarms and performance, which are not specific to OLTs, ONTs, and services, actually, which are general to the pod. After that, we have APIs for OLT management, where we can provision an OLT, retrieve what is there in terms of OLT, retrieve some hardware inventory information about the OLT, and also we can retrieve a list of OLT NNI and POM ports. And we can even manage the software of firmware of the OLTs. We can do some upgrades using the APIs. We can reset, delete them, and some run available diagnostics and retrieve results. And after that, we have APIs for ONT management, where we can, again, like the OLTs, we can provision new ONT hardwares and update what is there. And it's important such that it gives the ability for the operator or for the user to replace a faulty ONT, for instance. Then we can, again, retrieve a list of what is there as in terms of OLT. We can get rid of the list of ONT UNI ports. We can, likewise the OLT, we can upgrade the ONT firmwares and also get what are there in terms of the software. We can, again, restrict the ONT, delete it, and run some ONT diagnostics. And also we have some if we can go back to previous, please, Andrea, thank you. Also, we have some slides for service management, where we can provision new services, enable them, and also list which services are present in which ONUs actually. And also we can define, create new technology profiles. This, this is an abstraction for being able to support different technologies, access technologies in SEBA. So we can create, manage technology profiles, create new service definitions, list all of them, and also list speed profiles, and also its service subscriptions. So these are all the APIs that will enable you to be able to integrate to an OSS-based software operator without hopefully thinking other things. So thank you. This is my end of my part.
So thank you, Burak. Then it's my turn to give you an update on the Broadband Network Gateway. And we did in the RD 2.0 some significant updates in terms of conceptual work to understand how we could manage and enable it. But first of all, let's start from where we were before we started, and that was that in the reference design 1.0 we have introduced an horizontal separation of the broadband network gateway into two parts. That is on one hand side the service edge, on the other side the routing part. The routing part is the attachment to the core network and provides routing functionality of customer traffic. And the service edge is the important element which terminates typically customers, which grants them access to the network, which provides them access to their services, and also provides the quality, ensures quality for services for the internet connection, and on the other side also enforces regulatory things like accounting, like legal intercept. So this has been described. That is what we could call a horizontal separation between these both, which is very much focused on this functional thing. In the update to version 2.0 of the reference design, we have looked more into the vertical separation based on the CAPS design principles, which are outlined by the Broadband Forum standard TR459. And we have tried to understand how this work of the BBF maps to a world where we are coming from a more data center oriented focus, and especially how this would interact in a world where we have SDN controllers. So this has been essentially a more conceptual work, where it's no formal specification of APIs or code. We are working on this in the next steps. But before we could start, so we had to make clear where are we, what is required, and what do we need to implement. And based on our analysis of this BBF work, we follow essentially the design principles of these three important interfaces which are designed. That is a management interface, which configures and manages all the general aspects of the hardware, of functions and programming. Then there is the state control interface, which is programming the forwarding for specific users, for example, after granting them access, programming forwarding rules that they can access IPTV service or multicast services. And then there is the third interface, that is the control packet redirection interface. That is the one which is which you can think of a control plane between the separated control and user plane, and forwards all the control plane packets from the user plane to the control plane, so that the control plane can take care of these control packets and decides what's to be done with these. Based on this high-level architecture, we have asked ourselves, how would we deploy this concept? How would we enable and control a BNG control plane for the subscriber edge together with the user plane? And how does these three interfaces fit to the world that we are working here in around an SDN controller? And I'm going into this in the next slides, but before we do so, where I have to also say that this work is seen as a complementary thing to the TR 459. And we are working in this in a separate, smaller project group called TASSEN to see how these BNG UPF data plane abstraction could work with the tools that we are used to here in the ONF with the gRPC and P4 runtime. And I'm also spending some words on this activity later in my talk, in my part. But first of all, let's move to the next slide with these deployment options of a disaggregated BNG. So essentially, there are 3 deployment options. And I will start with the top left one, which is called the native BNG. And where the idea is to do straightforward the work how in past is done with an SDN controller, and that is to integrate the BNG service edge functionality as a kind of app or plugin on top of an SDN controller. If you do so, in principle, all your 3 interfaces that we have, the yellow, green, and the red ones, will have to speak directly with the SDN controller, and the SDN controller will program and take care that everything is enforced in the user plane. This is a very simple way, but has a number of drawbacks. For example, that all the traffic has to be forwarded through the SDN controller, or at least it has to be passed through it. And this might turn out to be a little bit limiting in terms of bandwidth and in terms of handling, and might put pressure on the SDN controller that's not necessary. So one of the alternatives would be to move into a more standalone way, and that is essentially in the lower left part shown, where we in principle separate the control plane part from the BNG service edge from the SDN controller itself, and only manage all the things which are not needed to forward traffic between. So there are in principle 2 options. That is that the management itself on the left side is still the management, and also this state control programming is still going through the SDN controller, and when it's enforced on the user plane, that has the beauty that the SDN controller knows about all the things and can correlate to for example, other alternative control planes which want to use the user plane. So, for example, if a mobile core is deployed on parallel of a BNG on the same hardware. But essentially, what we are doing, what the improvement is, or the beauty is that you have to have a control packet redirection. So the forwarding of the essential control plane packets is outside of this SDN controller. On the right side of this lower left part, there is the alternative where the control plane is essentially directly connected to a user plane, but this still would mean that you need a policy enforcement that the SDN controller can take care of this and has overall the master management or master control about the user plane. So for example, if you have, as said, you have 2 different control planes trying to access the same user plane, you have to manage in between them. So that none of them is taking more than it should be, and you can ensure the quality that is required in these elements. Still, this would mean similar to what you see in the native, that you have to agree on a set of interfaces, and this is all still one of the challenging things. On the top right part, we have the other alternative where we essentially collapse everything into the user plane device itself and run the control plane inside the device. We are assuming here that this is, for example, beneficial in very, very small deployments where you don't need a specific SDN controller or just a simplified control layer. But it's most probably only a smaller part in the deployments. Overall, what we conclude from this is that there is not really a golden solution so far. We have to follow up on this and see what really works out in practice, and where we can move forward with this. Can you switch to the next slide, please? One of the things that we learned and looked into the course of trying to understand how this BNG could work in these contexts is that we have seen that one of the biggest problem and biggest challenges is to write one application which works on all the different silicons and is running on the same performance. So that is when our target with the TASSEN project, where we try to look how we could achieve an programmability level similar to what we have before, and leveraging also the performance and the different hardware variants, and still have some abstraction which provides some silicon independence and freedom of implementation. These ideas are based on what we have learned from the OpenFlow experience. So that essentially, if we are going for a more formal specification of a forwarding pipeline, is a very essential step and helps to enable more hardware varieties to do and give the control planes a freedom to choose them, similar to what could be achieved if the BBF caps concept on a different abstraction level. On the other side, as I said, what we are looking into is that we try to use proven cloud technologies like gRPC or P4 runtime, and try to add everything that is missing to enable it with an operator use case. So essentially, these pipeline data models, and we are working on this. And in a very small group. This group is open to join. Just drop us a note, and we would be happy to introduce you to the work, and would be happy if you support this work. Overall, as I said, we see that this TASSEN concept is complementary to the BBF-based approach. The so-called distributed BNG concept, or with CAPS, is essentially focusing on the PFCP protocol, which is the standard in the mobile world for disaggregation CAPS, and this is reused by the BBF also in order to smooth the migration to fixed mobile convergence or wireless convergence. What you have in this concept is you have a control plane which communicates to a user plane, which we added a small C on this. So it's a distributed BNG user plane control part, and the real user plane part is below and in the lowest part. And this user plane is broken by a PFCP, and essentially is when using the user plane BNG to program all the necessary things. So essentially it has an interface to chipset SDKs to program it. Our approach on the right side of this is a little bit alternatively, and we are going in direction that TASSEN might work below this distributed BNG, or might be directly programmed by a native TASSEN compliant BNG control plane, but we are not actively seeking this implementation right now. The TASSEN itself is this red part in the middle of the architecture, which in principle provides a logical to target mapping between the pipeline data models and the specifics of the user plane, so essentially the chipset SDKs. So that's it from my side on the no, it's not. That's it for the broadband network gateway. And I'm also happy to share the update on this new element that Burak already introduced with the device management, the device manager and the device management interface. That is a new element, and as Burak introduced, it came during the implementation process, and the essential function is that it's providing some support in the general device management. So you can see here the inventory management, hardware configurations that are not access specific. So it's the access specific things are done in VOLTHA, and not but the device specifics, like software updates, like this mentioned inventory, like the reboot of a device, etc. This is done with this device manager. It follows also standards and uses the data models outlined in the respective IETF and BBF drafts, but it's implemented in a different way. So the API is implemented in a different way, even if the same data models are supported in the end. So, and now it's really my turn to hand back to Burak, I think, and to present on the VOLTHA scaling improvements.
Thank you, Mario. It will be me actually who will do the presentation. Thank you. For this section, like I mentioned in the beginning, scalability work became a part of this documentation. To be honest, it wasn't our first intention to include this section when we started to work on this reference design. We are aware that scalability requirements are mostly deployment dependent and heavily depends on the network architecture. But this has changed after some extensive work done regarding the scalability issues. And we decided to add this part because it introduces a new concept of scalability. Before I go and explain how this new implementation is done, I want to first explain the necessity of it. From the first reference design study to date, we discovered that the scalability of VOLTHA components for higher number of subscribers or flows couldn't match our requirements. What has been foreseen about the scalability of VOLTHA components in theory didn't match the practical use cases. So I guess this is the time for me to share what were those initial needs for operators. We wanted to have multiple OLTs to be controlled by a single server cluster. So the control plane components should have harbored many OLTs, including different vendors, where on a single OLT, all of the ports should have been used with the same or different vendor ONTs. And more than one service should have been created for each subscriber. Having said that, the old VOLTHA stack wasn't suitable for that. When we did the testing with simulation tools, we found out that the scalability of two topics couldn't be matched that are requirements actually. The first thing we've seen that it wasn't scaling well on single OLT with multiple ONTs. And the second, there was something missing for multiple OLT in a single pod scenario. And this made us to reevaluate how the VOLTHA stacks were implemented. After some serious design discussions, it's been proposed to implement the stacks in a different approach. Since the horizontal scaling preferred to simplify the operations, we created an exemplar implementation which supports this approach. And now it's been tested that with the new developments on the adapters and with the new design approach, the platform meets our requirements. And we call this new approach per OLT VOLTHA stack model. By the way, I should also mention a VOLTHA stack consists of the following components, which are OpenFlow agent, RV core, OLT adapter, and ONT adapter. So what it does, it's basically with this proposed implementation, a VOLTHA stack is built for each OLT. Therefore, when you need a new OLT in your network, you just go build a new VOLTHA stack. Or this also applies for the removal process as well. When you want to remove an OLT, you just remove the related VOLTHA stack. this new approach helped the multiple OLT scaling in a single pod. This can also be applied for ONTs, the horizontal scaling part. In every VOLTHA stack, there can be more than one ONT adapter as well. And this we see that this helps the scaling. This design currently, by the way, doesn't support HA structure on VOLTHA stacks, and it relies on the fast fail restart method, which seems to be okay for now. But still, each VOLTHA stack is connected to ONOS in HA structure. So this sums up this slides. Maybe we can go to the next one. And on this next slide, I would like to explain TT SEBA structure and what we did on our live network, actually. You can see that there are two parts of this design. First, I will start with the physical design. TT puts a tiered architecture for SEBA. We believe the multi-edge clouds will be reality in near future. So we start to do our implementations in a way to support future networks. So basically, we are using some tiered structure for central offices. On the edge sites, OLTs are put right now, and on some higher level, there will be control plane clusters. Those control plane clusters will be placed in a more centralized manner than the OLTs. Hopefully, it will share its compute power with all of the virtualized access networks in near future. And at the top of all, there will be some management domain which we call SEBA Central. And this is something we are proud of, actually, because this is the point both logical and physical integrations are done with our OSS BSS systems. After big components like VOLTHA, ONOS, open source adapters, and etc. are matured enough in the ONF, ONF just laid us fundamental for SEBA platform. Therefore, we had a chance to focus on how to use this platform on a massive deployment scenarios. I won't be explaining the black boxes inside the logical architecture, which are pretty self-explanatory, I think. But I will talk about those warm yellow boxes. SEBA didn't address a management tool for the operators, at least the way that we needed to. And this is an understandable thing since most of the operators have different needs from such kind of a tool and the developments. And it would be hard to melt every request of operators in a single pod. Of course, it provides the necessary tools like MBIs, but as operators, we need something else. And their NetSIA with SEBA Plus platform filled the gaps for us. The capabilities of the platform isn't restricted by just management, but I won't go have time and detail explain all of it. So anyways, I want to go ahead and talk more about, talk more about what we needed. Basically, we needed a tool that has some clean, understandable user interface, where we can follow the alarms and metrics and do all of the FCAPS related operations as we already do with the legacy networks. We also needed a provisioning and service logic tool. And finally, we needed to have a single point of integration with our OSS and BSS systems. It's a still growing platform, but for now, it does support what is needed. And this sums up my part, and I want to leave the stage back to DT to hear more about their progress. Thank you.
Thank you. And yeah, it's now my pleasure also to provide you some updates on where we are in DT with the implementation of SEBA, and then where SEBA plays a role in our network. But first of all, let me introduce you one of our biggest innovation projects that we have in DT, and that is Access 4.0. I would believe a lot of you have already heard about this, and but still I want to spend some words to get you a context where SEBA plays a role. So Access 4.0 concentrates on the access networks, which are essentially compromising on the access technology devices, so DSLAMs, optical technologies like GPON, OLTs, etc. And on the other side, also the BNG, where we terminate customer access and enable all the functionality that a customer can run to the internet. Access 4.0 is trying to renovate and innovate here in very different angles. So the dominant is one of the dominant things is presented here, and that is that we implement disaggregation in a way that we separate hardware from software. So this is all the blue elements are well known. This is where the VOLTHA plays a role, and we separated the OLTs into two parts. When the BNG is a bit hidden here, as these are the green elements on top, and if you see here, there are spinal leaves, and this is replicating the idea of a data center inspired leaf spine fabric with some smaller twists, like that the spine switches are not just a kind of backplane of for connecting the leaves. We also use it to connect to the IP core. So essentially on the spine switches is the routing part of an existing BNG. But more important is also the service edge, and here this one is hosted on what we call leaf or the top of the rack switch, and to attach to them are all the different access systems, the GPON systems. You can see here also some of these functionalities, as I mentioned earlier, that are important to the BNG, and that is providing wholesale access to other partners. There is the legal interception. We have also the connections to our management networks. And one of the things that is hard to show is the transformation in the software stack and all the software elements, and how we operate this whole new thing, and that is completely automated and software standard according to how normally today you would design it. We have on the left side these three mentioned these three servers. These control local management on x86. These are local control management planes, and all the software for this is developed new in a completely different way. And there is another counterpart to this, to the OSS BSS, and that is the central management layer. This is essentially what is running, and it's not just theory, it's already deployed in our live network as an MVP since December 2020 with the first customer, and up to now this customer has a constant connection and no breaks, and it's really a verification that the concept itself works. So introducing or repeating somehow the Access 4.0 concept, let's move to the point where SEBA plays a role in all these, and this is on various elements. We have on the left side, the one hand side, the PON part, which is quite a lot influenced by the developments at SEBA. So we have this multi-vendor PON. We have all these Northbound abstraction using the complete VOLTHA stack with the SDN controller, the drivers, the common controller management, etc. And we have also well-defined interfaces which replace the typical EMSs, and this is also implemented with full automation and available as a workflow on one hand side in ONF, but also on the other side in the broadband form, the standardization organization per se for the access network. So this is one big block which is very much based on SEBA, and on the other side is these activities around the BNG. So as you have seen in the previous slide, where we implemented the BNG as a fabric design, similar similar and inspired by the core architecture from the ONF. We are implementing these with the open hardware, and currently we are deploying the software from a company called RT-Brick for the fabric itself, but also for the BNG parts. And that is what I would like to highlight, is that we are working together with a number of operators to create an open BNG community. And this is the idea is to strengthen here and leverage the scale of all the operators and combine work in the broadband forum for the standardization of the architecture. Also, we work in the OCP on open hardware, the ONF, we work on what we are looking here, have seen on the TASSEN project and also with what is done in the telecom infrastructure project. I would like to stop here and hand back to Andrea, I guess.
Yes, thanks, Mario. That's going to be me concluding the presentation. So as we all saw with the great contributions and the great status of the reference design 2.0, there's still some room for improvement and some next steps that we want to take as a reference design community. And we want to codify and have more thought and a more well-defined FTTB discussion and implementation in the RD and then in the code. We want to include parts of EPON, especially for the Asian Pacific market, such as Japan or Korea. IPv6 is definitely something that will come as a big part in the future. And also the MDU is something very important for our operators. Obviously, this roadmap is driven by our operators and partners and supply chain. So if you're interested, come and join ONF, come and join this community to drive your requirements within the reference design and drive the reference design even further to a bigger and broader adoption. Because really this is a collaborative effort. It's a collaborative effort between the ONF members, the ONF partners, the team here, but not just ONF. It includes OCP, it includes BBF, the Telecom Infra Project. All of these open source communities are really coming together in putting this solution, starting from the description, then to the implementation, then to the deployment. And this is a reality, as we have seen in the Turk Telekom and Deutsche Telekom deployments. This is great. So a few useful links and references for this presentation. You can find the Reference Design 2.0 at that link. We will share the slides, so don't worry about that. We have included also the ONF TASSEN overview, the TASSEN repo, which for now is member only, but will be open in the future. 2 articles that outline the Deutsche Telekom and Turk Telekom deployment, and a little preview for everybody that joined. That was my small token of appreciation. We're going to release the VOLTHA 2.7, which is part of the implementation of the SEBA RD Reference Design 2.0. We're going to release it today, and that's the release notes. So a little token of appreciation for those of you who joined today. If you're interested, just go ahead and you could read those. So having said that, I would like to thank everybody for joining. There are a few emails here that you can take note of, and you can send us questions and comments. We still have some time. So what I would like to do now is I would like to open some questions and answer time. There's a button in your bottom of the screen at the bottom of the presentation. It says Q&A. Some of you have already found it and have already used it. So please do send over your questions, and I'll be curating them, and the presenters will be answering those live. So a few of those were already answered. One of them I'd like to elaborate on, which is the question was, with some of the most known ONF projects diverging from OpenFlow towards P4 and P4 runtime, would it make more sense to use the P4 runtime as the northbound interface for VOLTHA as well? Are there any plans to evolve in that direction? So indeed, yes. There are some thoughts about moving VOLTHA from OpenFlow to P4 runtime, but really the move needs to come with tangible benefits. At the moment, there is really not that much that OpenFlow cannot do for the VOLTHA use case, meaning we have not yet hit a functionality except maybe a few configurations of lag ports that could not be done via OpenFlow. So I think OpenFlow suits us fine right now. What we are thinking of is possibly moving Northbound of VOLTHA to P4 runtime in what we call VOLTHA 3.x, which right now we are at 2.x. 2.x is in production. 2.x will become long-term supported in one of the next releases. So that's what we are focused on right now. There are already some thoughts about a newer version of VOLTHA, one of which is using P4 and P4 runtime. But just not to forget that the important part of the P4 runtime is not just the P4 runtime protocol, but it's the P4 specification of the pipeline. That is the key. The protocol is just a means to an end. The end is the capability of programming the pipeline. So if we end up having that need, we will go to P4 and P4 runtime. But at the moment, OpenFlow suits our needs fairly well. The other one, which is still is a little bit a keen forward thinking to VOLTHA 3.x is with a per OLT VOLTHA design, would it make sense to have fewer layers and putting them, some of these pieces directly on the box? Yes, it would. There are some constraints on hardware, on the requirements to support all the PON ports. You would still need some pretty powerful CPU to have that programmability and what is VOLTHA right now. But yes, there are some thoughts of trimming it down, slimming it a little bit and putting it on the box directly. But again, that's a forward-thinking VOLTHA 3.x or even further discussion. So a few other questions that were open right now is, can the presenters comment on software stability and early deployment experience? I would like both Turk Telekom and Netsia and Deutsche Telekom to comment on this. So Samil, Burak, do you want to start?
Of course I can. Well, this is actually a big topic, but for a short answer, I can say that we are in a much better place than we used to. We actually in a year or so we have much more stable code bases, I believe, because we are currently trying these codes on live customers, and we don't see any stability issues that cause any service interruptions or something like that. It was a little different maybe last year, but it's a fast-growing platform, and I can say that we are in a much better place right now.
Yeah, and if I would add something to Jamil for our deployment, I would say it looks quite the same. So as I mentioned in the presentation, the customer is still alive and connected. Maybe we don't recognize if he can't call us. No, just kidding. Well, it looks we are really in a good position. It works. There are still things to do and to improve. And so, but overall, we are quite happy with the actual state.
Okay, thanks. It's great. And just to mention, some software stability and soaking experience has been tested at ONF as well, meaning that we do have a series of nightly tests for VOLTHA and a series of soak tests where we let the code run, and that improves the stability greatly and the scalability greatly as well. So another question that has been asked is, and I would like a little bit to elaborate on that, is how about XOS is still used on NEM? I'm going to take that. We still do use it in the example platform of SEBA. The operators have chosen their own edge controller that manages the end-to-end solution, mainly because they also have some of their specific pieces, for example, the BNG that Mario spoke about, and they would like something that was capable of controlling all these pieces, and thus they have gone for their solution. Is that a right way of describing why the operators chose some pieces such as VOLTHA and ONOS and maybe not others such as XOS? I guess the silence was a yes.
Yes, this means yes. Unfortunately, I cannot comment on this. I haven't been involved in that decision, so very sorry, Mike. But I could take this question and then relay it to the people who know better than me.
Yeah. A few other open questions, and that the one was related to OF-BAA in terms of the relationship with BBF work and OBBAA and SEBA. So does anybody want to comment on this one live?
Yeah, yes, Andre, I can comment on it. Actually, I tried to answer it, but I couldn't do it because I need more space. Actually, yes, they are really related, actually, and we have been trying to work actually in BBF and trying to align these for maybe since last year, and maybe if you there was a presentation that I made actually in the last year's broadband event, talking about the ONF and the BBF. I mean the SEBA and the Cloud CO or OBBA. What is important in OBBA actually are the interfaces that are defined between the devices and the OBBA, and also the interface between the OBBA and the STN controller. These interfaces that are specified are important actually. And you know that BBA is doing a good job in making and creating the specifications. And we always know that the ONF is good at providing the software and the implementation. So we have been working to get these specifications actually and try to work them so to be able to be compatible to a wider range of devices and controllers actually. So they're very related, very important, and we are working on it, but it's not that easy, I should say. So that's a better answer, I guess. Yes. And it was a great question. Thank you for that.
One question where I think we could elaborate a little bit more is, it was asked, is there already a commercial product compliant with RD 2.0? Well, the RD 2.0 encompasses a lot of elements. What we have at ONF is what we call the continuous certification program. And for the VOLTHA piece, we are certifying some OLTs and some ONUs that are tested nightly within our Jenkins suite. And that certifies that for that specific VOLTHA release, they are compliant. So you can find it, it's up on the web, and it's called continuous certification. I also know that Deutsche Telekom developed in collaboration with OCP the specification for the OpenBNG device. Mario, maybe you can comment more on that.
Just a second. Yeah, indeed. I think we not only developed an OpenBNG, we also developed an OLT.
Yes.
So and all three are already available. Are going to the BNG. I think is not yet available on the OCP, but it's going to be available as soon as the anticipated chipsets are available for that device. There are some minor things. What we essentially created for the BNG are two devices, one for the leaf, one for the spine very much complementary, trying to follow the idea that I've outlined with the Access 4.0.
Okay.
Well, on the other details, well, lots of details to discuss about these devices, but maybe too much. We might have other questions. I'm also trying to answer some here, so sorry.
Yes.
But that one.
So I think we have. I have time to clarify maybe a couple more questions. There's one from Hagen, which would require a longer answer. So I'll take that up after the meeting, and I'll make sure to get that reply to you via email. So there were a couple of questions. One was kind of related to access technology per se, which is there any collaboration between ONF and ORAN? Yes. I'll be more than happy to forward you a lot more of information after the meeting. We are actually an ORAN member, and we are developing RAN-specific software in another project. I'll get you some more detail about that later. And the other one is we have mentioned the Asia Pacific region. Do you see some initiative in the Latin America region? Indeed, we have seen some interest from some operators in South America that have started the testing with our software. And so there is a little bit of traction over there. It's still in testing phase, not deployment phase, but we have seen some initial work. What I have to say, and I have to thank both Turk Telekom and Deutsche Telekom a lot for this, is they have paved the way, meaning that they have really stood up and said, this is doable, this is something that we can think and we will deploy. And by them committing this much resources and this effort and standing by this project and this reference design and its implementation, we have made great strides. And now a lot of other operators are going to reap the benefits because of these two very strong champions of the reference design and the implementation within VOLTHA, ONOS, and the rest of the code base. So Marius, Emil, Burak, any final words before we close?
Maybe I want to thank actually the guys that was in the team. I wanted to do it in the beginning, but it's a good place right now. Maybe I want to thank Manuel, first starting with DT, Manuel, Björn, Mario, Olaf, and Hans-Jörg. Thanks, guys. And NTT, Kota-san, it was very nice to work with you and the others. In Telecom, yes, it was always good and great to work with Cemil, but I'm going to skip it. And from Sienna, David, thank you for your efforts and help. And also from Redisys, Vayesh, and Sean, thanks, guys, for your help and support. So that's my ending, I guess.
I have nothing to add. Just thank you for being here and listening us.
Yeah, same on my side. Burak, thank you very much. I also have to thank you all the people mentioned. It was great to work with you on this thing, and then let's see what how we proceed with this.
Okay. Thanks a lot, everybody, and we'll talk to you in the next webinar. And if you have any questions, feel free to reach out to us at the email that you have seen on the screen during the Q&A session. And the recording will be shared, as will be the slides. And a personal thanks to everybody who joined, and I'll talk to you next time. Bye-bye.